All right, we have talked about how to do transformations for either response Y or the predictor X. Um, and now what if we need to transform both X and Y? Okay, so in the case that both X and Y are skewed and they are not really close to normal and they need transformation. So you have these two approaches to choose from to transform both X and Y. So the first one is that you transform X so that the transformed version, this psi S, is as normal as possible. So you just use any of the previous discussed method, power transform, BothXY, or even a square root can make X closer to normal. It would also work, but normally we just use BothXY or power scaled power transform. And then consider doing a simple linear regression with a transformed X. So this beta 0 plus beta 1 times this psi S, which is a transformed X. So you first do the simple linear regression and then use an inverse response plot to decide the ideal transformation for Y. Basically, you find this inverse function of G with this result, beta 0 plus beta 1 times psi S. That's the simple linear regression with transformed X. So this is approach 1. And a second approach you can take is to do a multivariate version of the BothXY to simultaneously transform X and Y to normal distribution. And again, you can use this power transform function in the car package in R. Let's look at an example. So this is using the government salary data. We want to use this data to predict max salary using this predictor score. So these are the diagnostic plots of the model with the original data, so not transformed, where we can tell it has non-constant variance and not really normally distributed error. Right, there are some pattern. It's not a round shaped cluster here. So anyway, we need to do some transformation actually for both X and Y, which you can see here. And obviously that X and Y are both right skewed, and there are some outlier issue from both this box plot and also this QQ plot. Even though this score looks better, but not ideally normally distributed. Yeah, so we would consider transform both variables. Let's take the second approach first, which is a multivariate BothXY transformation. This is how you can do it in R. So I named this transformation being trans XY, which is this power transform. I combined these two variables together and regress on one. See, and do a summary of it. And this output suggests that we use lambda equal to 0 for the response variable 1. And we use lambda equal to 0.5 for the predictor X. Remember that lambda equal to 0 is actually corresponding to a log transformation, right? And also, again, this summary would also tell you likelihood ratio test. But for now, we just need these two for the transformation of the variables. So we're going to take the log of the max salary and take the square root of score. So power 0.5, which is square root, right? Let's look at how it does. So this is the original fitting. This is after the BothXY transformation. On both y and x, looks much better, right? Data are more close to the regression line, and they are like evenly, more or less evenly distributed around this line. Okay, so this is with approach 2. By the way, I also plotted the diagnostic plot. And this is with the standardized residual. So both are from the transformed data regression. So this is the standardized residual versus the transformed x, and this is the square root of the standardized residual. Both looks good, even though there is a little bit of downward direction for this like blob here. Okay, let's look back to approach 1. So this is a reminder, like what is this approach 1? We transform x first with power transform or BothXY, and then we consider doing a simple linear regression with the transformed x, and then use an inverse response plot to get the inverse function for g, right? Okay, so this is showing you refers to the transformation for x, right? Again, it suggests lambda equal to 0.5, which is just a square root transformation for x. So yeah, lambda x equal to 0.5, and once we transform this x, taking the square root of the score, and then we need to find this g inverse. So we do the inverse response plot on the transformed x. Well, the next slide here showing you the inverse response plot with transformed x. So basically have y hat, like being on the y-axis, and the y value on your, this is on your y-axis, and on the y value on the horizontal axis. And again, this different color of the lines corresponding to different value of the lambdas, lambda hat, and this, again, this black line fit our, oops, no, not really the black line. Yeah, black line looks okay, and I think this pinkish line fit the data the best. This black line is not bad, but you can see that this lambda equal to 0 corresponding to log of y fits well. So for this pinkish colored line, we'll follow the test and run the value to 0.25, and also not strictly necessary. So this is from the result from the book. So yeah, let's see how it does. We do this transformation of y to the power of negative 0.25, and again on the transformed x, which is the square root of the score. Well, the fitting looks good, right? Even though it changed the direction comparing to the original one, because we take the power of negative 0.25, which changed the direction of this y. Yeah, so yeah, let's look at the diagnostic with this with this approach 1 transformation. Well, this one looks okay as well, but it shows a more steep downward direction for the standardized residual. which means there is a little bit of trend here, even though it's not really obvious. So if we compare this approach 1 and 2, we see that both approaches gives the transform variable that are highly normal. And in this case, approach 2 gives slightly better consistency of the variance of the residuals. So, well, for the approach 1, it had more obvious downward slope. So in this particular case, approach 2 might be a better choice. But in general, these two approaches lead to essentially the same answer, but approach 1 tend to be more robust. Because like when you do BothXY, multivariate BothXY, it's susceptible to outliers, sensitive to outliers, and it can fail in that case. Well, approach 1 will still give you reasonable results. So that's what I mean, like saying approach 1 being more robust. Yeah, and well, again, this BothXY method was designed for non-negative data. And remember, it's for strictly positive and monotonic data. But it's also possible to try use it if there are only a few negative cases. So there are, so the first approach that if there are a couple of negative values, you can just add a small amount of value to your data. Typically, this value is just small, like 0.5 or 1. But if your data is in general, your data is small, so you should add a value much closer to 0. Or you can use one of the power transform with the family options. So family can equal to this BCN power or YJ power. So this is J. This font is a bit tricky for this J. So this is Y and J power. So these are the options that you can specify when you run this power transform. Then it should work for if you have negative responses. Well, I have some R examples follow this. Let's take a look for transforming both X and Y. So in this example, let me enlarge it a little bit. Yeah, in this example, we transform both variables, which are body and brain weight in mammals. So the data I got from this person, and also you just attach this library and you will find the data from it. Well, so I attach the data again just for easier access to the variables. And if you take a look of the data for the first few records, so when you do the head of the data set, you will see the first couple records is like this. You have brain weight and body weight. So first of all, do a scatter plot, right? This is how we do it. Label X and Y and the plot. The regression line, well, not that good comparing to like when you fit the data. So residual plot, well, residual plot is like this. Apparently, it's not like stable variance. Well, and in this case, both the X and Y are positive. So we can do this power transform and find what's the optimal lambda. well, both suggested lambda equal to 0, which corresponding to a log transform. So we just do the log transform on both. We rename them as brain, ln, and body, ln, mean log. So we do the transform data regression, and this is what it looks like. Much better, right? And let's look at some of the diagnostic plots. The residuals are okay, if there is no trend, and the variance looks stable, and the QQ plots looks okay. Even though always the tail will be a little bit off, but this is close enough. And this one is all right, and we have no outlier. So this is it. When we do this log transform, we get the regression we wanted. Yeah. So, well, again, I have another 1 or 2 examples showing you like when the data are really not linear, they do not have linear relationship. Basically, you do not have much of choice doing transformation to make them to linear. So in this case, you would have to do something different. So we've seen this before, like this is when we talk about a bad leverage point and good leverage point. I think that's when we introduced this example. So I plotted this 2 set of data. So y bad and y good regress on x value, and you notice this one will not fit with a straight line. So in this case, we would have to use some quadratic line, like a curve, to fit this data. And well, for this one, because it has strictly positive value to transform, and we happen to already know it's true, it's non-monotonic. So we just manually use the LM function to fit the model but actually this is the case when we have multiple linear regression. You see, I added even though I name it transform, but this is actually a multiple linear regression. Well, I added this term x squared. So again, I have to use this I here with this bracket in order to introduce this term to our LM function. So yeah, or we can just put this x underscore sq here. But if we want to use this directly, we have to specify this I with brackets. Well, so this is what it looks like, and those are the summaries. You're all familiar with summaries, and also this is what it looks like with this multiple linear regression. Right, this is when you will not fix this regression by doing transformation, but you can do something like this to make it fit well. Yeah, so the example 6 is another one that you can read. About. I'm not going to go through it. I believe you will see like what transformation we're going to use, and it's kind of a practice, but with the answer on it. You can just go through it and find out. Yeah, I guess that's all for our examples. Well, in the end, I have this summary chart for you. I got this from the book. So, so when you think about diagnostic of this simple linear regression model, and it's better to keep this in the back of your mind. You do not really need to do every step each time you fit a linear model. but it's nice that you go through this flow a couple times so that you know what to think about when you look at the data and look at your model. So first of all, we always do a scatter plot of the data and get a feeling if it's really linear or not. And see if there's potential problem with the data, outlier, or whatsoever. And then we fit a model based on subject matter expertise and or observation of the scatter plot. So we fit a model after doing a scatter plot, and you will assess the model in particular. Is the function from the model correct? And do the errors have constant variance? You do like diagnostic plots, and looking for leverage points, outliers, and if there is outliers or bad leverage point, like what you do. If there's no outliers and leverage point, you also consider, is the sample size large enough? So if it's large enough, you can do the test and see, okay, if there is significant association between Y and X. Right, when you do the test, we have, again, so when you do all the inferences, we have this LINE, all this for assumptions, right? So we have to get close enough to normal, and you have, so the sample size matters in that case. So well, there are like more complicated things, but I believe we have covered all of this. And for this bootstrap, we haven't talked about, but I'll include that in the later chapters. Well, yeah, I guess that's it. So again, this flow chart would be really helpful to keep it like in your mind. You should think about it when you build your model.